there are acknowledgements kind of peppered throughout here and a long list at the very end. But I want to make the point here at the beginning, everything that I'm showing you today is collaborative. It's a group effort, and some of the key collaborators in this, Brenda and both of our students here at the University of Utah, the Returning Rapids Project, amazing group of folks that I'll talk about here in a second, and the Utah Water Science Center arm of the USGS. Again, Casey and Scott, some of our own alum, are really instrumental in dragging me into this, okay, into the mud. So a couple of little like factoids about Glen Canyon and Lake Powell. Location-wise, of course, we're down here. Powell is the second largest man-made reservoir in the US after Lake Mead, which is its downstream neighbor on the Colorado on the other side of the Grand Canyon. Powell formed after completion of the Glen Canyon Dam in 1966, and ultimately up to 650 square kilometers of the area of Glen Canyon were inundated during the high stands of the 80s. Nearly 90% of Colorado River water originates in the upper basin, which is a semi-arbitrary regional area that's depicted right here. That water is used and shared by 9 basin states, 29 federally recognized tribes, as well as parts of Mexico. And a recent study out of Utah State estimated that 74% of direct human use is going to irrigated agriculture, mainly cattle feed crops in the Imperial Valley and Coachella Valley area of Southern California. So in the drought-plagued American West, right, amidst increasing demands on water and population growth and so on, water is king, and not surprisingly, this is what most people think about when they think about Lake Powell. There are other aspects and resources associated with Glen Canyon Dam and Powell. One is the power plant, 5 billion kilowatt hours. I'm not sure if this is true still, but historically generated annually. In February of 2023, we came within 32 feet of the minimum pool level in Powell that is needed to provide that power. And the Bureau of Reclamation is predicting, and this is their kind of best case scenario, or well, not best case, medium scenario prediction for this winter, that we will get fairly close to that again this winter. Some people are starting to talk about minimum power pool as effectively dead pool, I think, because it's not clear that we will be able to get the turbines going again if it drops too low. So, you know, interesting times in terms of that aspect of the resource here. There is also the harder to quantify resource of recreation. My computer hasn't frozen yet. Go like this. Right? The Glen Canyon National Recreation Area sees millions of visitors per year, and it is, of course, situated in southern southeastern Utah, surrounded by national parks, federal lands, protected areas, and areas that are at risk in terms of their protected status. And so there's that whole aspect of this field area that I, again, just sort of innocently kind of got into. So who's in charge here? The set of laws and regulation and policy that govern the Colorado River operations kind of traces origin back to the 1922 Colorado River Compact. And today's use over the last few decades has been effectively controlled by the interim guidelines, which is a set of policies that were put together in 2007 amid severe regional drought and currently under intense renegotiation and scrutiny, because these interim guidelines are set to expire in 2026. So I don't know a whole lot more about it beyond that level of what's happening. And I know a lot of these conversations currently are happening behind closed doors. So I'm not sure that anyone really knows exactly what the status is here. So I'll just kind of step back and say this field area is sort of ground zero for a number of very complex, intricately connected societal, environmental, geopolitical, economic issues with many different stakeholders and at times competing interests. And that is depicted in a lot of the high profile news stories, documentary films, podcasts, and just public conversations that happen around Powell. And, you know, I feel like I've done some kind of interesting work in places like Mongolia, Straight Cliffs too, and I've never had the New York Times call me and ask me questions about any of it. But Powell is a whole different world. So career-wise, there's also been this aspect of it that's really interesting for me as I learn kind of the art of science communication. And it is very much an art, and I've learned lessons both the easy and the hard way through some of these interactions with the press and others. A lot of the conversations that I have with folks about my research here is kind of about what was gained versus what was lost when Glen Canyon Dam was created. And some of that is depicted here with kind of before and after photos. This is really where Returning Rapids, kind of their hallmark of what they do and kind of where they started. So Returning Rapids is a group of river guides who initially set out to document the reappearance of historic rapids that were starting to reappear as Lake Powell water level was drawing down. So they have all this beautiful, amazing historic imagery. One of the leaders, Meg Flynn, is a librarian and has access to and knows how to access wonderful archives of photos. And so some of what they do, a lot of it is kind of photo matching. And I love this one from Clearwater Canyon and Cataract with a 1980s high water level, you know, set of dinghies that have kind of come up from the lake to hang out in Clearwater. And here's the ledge that you see in both photos here. It's also worth noting that humans have occupied Glen Canyon for at least 13,000 years, I believe. And there are hundreds of known cultural sites that are part of that inundation zone, and who knows how many others that are unknown. So Returning Rapids is instrumental in access and sort of helping us define the problem. So they're much more than just photo matching. And I think one of the other angles where they've really been impactful kind of gets into things like advocacy and even decision-making processes. And the Northwash boat ramp is a good example of that. This is me telling Mike Dehoff's version of the story. We really should invite them for a DLS because they would give a great talk as well. But the Northwash boat ramp is just down from the Height Bridge, and it is where most of the Cataract Canyon river trips would normally take out. Here it is in 2006, looking like a perfectly reasonable boat ramp. The original Colorado River channel pre-dam was located over here, and it has sort of migrated over and started to cut into essentially bedrock on this one side. And when rivers cut down into bedrock, crazy things start to happen. So this is the boat ramp several years ago. And as you can see, there's boulders and ledges exposed. There's little bits of reservoir sediment over here as well. And this is a very steep slope, and you kind of go fast forward in time, and it's really comical. They call it CrossFit, Northwash CrossFit, because getting boats out of here is just craziness and physically hard, and also very dangerous and scary. So again, one of the many, many things that Returning Rapids does is try to work on these kinds of access problems and incorporating the science to the extent that it can be into the decision-making process. Okay, so we're here to talk about sediment. So I will start to move us towards the mud and the silt. Again, something that Returning Rapids brought to my attention is this Great set of quotes in an exchange that was recounted by John McPhee in an article called Encounters with the Archdruid. And it's an exchange between Floyd Dominy, who was the chief of the Bureau of Reclamation during construction of Glen Canyon Dam. He's shown here. Colorful figure, very vocal proponent of building this dam. And he's talking to David Brower, who was the first executive director of the Sierra Club and the first head of the Glen Canyon Institute advocacy groups. And they're arguing about the sediment and how long it was going to take to fill in Powell. And Domini's kind of saying that these reliable people don't know what they're talking about. But we know that at some point it's going to fill up with sediment, and who knows how long that's going to take, but it's not our problem. It's a problem for the future. And I purposefully chose a very apocalyptic view of reservoir sediment here in this little side canyon that we've studied, with wind blowing, and it's all like literally directly in your face that reservoir sediment is real. So some starting points of what we know about how much sediment is there. This comes from, again, the USGS had a major effort in 2017 and 2018 in particular, looking at running multi-beam bathymetry surveys throughout the whole lake, running some sub-bottom surveys, and then a major coring effort. And so, this is a map of Colorado River. The North Wash boat ramp is just down from the Dirty Devil River right here that we were just talking about. Here's the San Juan, which is the other major tributary that I'll talk about today. And this is the survey's sort of map of projected sediment thickness as of 2017. We also have, again, some depictions of the cores, the sediment cores that they took. And so the estimate there from the 2017 era data was that approximately 7% of reservoir storage capacity had been lost up until that point. We can decide whether that's a lot or a little. Who knows? We'll get back to it. Okay. Before then, one more thing, and just in the setup of this, I use that term experiment, and I want to talk about why I use that term, the Glen Canyon Dam experiment. To a stratigrapher's mind, right, this is a very well instrumented sedimentologic experiment. We know every day what the reservoir level is at the dam. We have river gauges in some really key areas that are measuring river height as well as discharge, water discharge over time. The USGS has this amazing data set where they've been able to map out the accumulation of sediment in deltas over time. We have satellite imagery because we live in the future, and we don't need a time machine like you do in the geologic record. If you want to know what it looked like in 2005, you go back and look at it in 2005. From a stratigrapher standpoint, this is basically like a large flume model. Here's an example of one of these that we spend lots of money as sedimentologists and lots of time and energy physically and numerically, computationally modeling systems like deltas. This is the Mississippi River Delta recreated in a big industrial building at Louisiana State. And so my naive, kind of approach to this when I started this work was, I've done a ton of work on ancient delta systems. This is the Panther Tongue Delta and Price Canyon just outside of Helper. That's an 80 million year old something delta. And I thought, if I can really test my assumptions around how deltas work in a really well-constrained system, then that's going to tell me a lot about the ancient rocks. So the present is the key to the past is the key term there. And in reality, we're kind of turning that around and thinking a lot more now about what have we learned from ancient deltaic stratigraphy that might be informative to this modern system. So it's always more complicated than you think it will be. Okay, so some of the guiding questions and approaches that we've taken here, it really, kind of goes back to my interest in signals and controls on sedimentary systems. If a sedimentary system changes, if a delta progrades, why? What controls that? Rates of both geomorphic and sedimentologic change is also really important. We have a wonderful opportunity to look at the sediment archives from two very different looking rivers, wonderful experimental data sets again. And I won't be able to talk more about it, but I would say that intersectional science and application in the public spotlight is also a really big part of this. So we're going to go on a tour, and I'm going to take you through a lot of work that we've done in the last 5 years, and it'll be kind of high level, photo heavy. If you're here for the graphs, there aren't many, but there's some at the end. I'll kind of judge my time accordingly, but I'll try to end up with enough time to really talk about the latest and the greatest, which is some of our bathymetry and sub-bottom imaging work. All right, so here's a profile of the Colorado River going down through Cataract Canyon with some of the key marker beds and elevations projected in. Here's Lake Powell at full brim, where lake level kind of hung out through most of the 80s, shown here. Minimum power pool is way down here. 2023 is marked here. And then we've got all these series of side canyons. Our tour begins below all the big drops and the exciting rapids. I always kind of, when we're doing a downriver trip, it's like, let's get through this so that I can look at the mud and everyone else is enjoying all the fun rapids and stuff. So we first started looking at impounded reservoir sediment in the highest zones here, near that full brim marker, near Imperial Canyon in Waterhole, or Calf Canyon as it's known. So this is what the section looks like. We do sedimentologic things, right? We go out, we measure section, we measure the thickness of these beds, the grain size of the beds. I try to determine what the environment was of that given bed. Hopefully you can see some of the cyclicity that's implied here. There are these kind of tan colored sands that then are capped by kind of a harder, more indurated unit. And then you kind of see that sand, mud, over and over again. So, we looked at this fabulous sedimentary structures, climbing ripples, wave ripples, root marks that are coming down through what we interpret as lake beds, showing Tamara's colonization after the water level came up and went back down. It is just a full-on absolute wonderland. Interestingly, for working in decades-old sediment, the mud is really, really hard. The sands are less indurated, but this is actual rock until it gets wet. And then it becomes just sludge. But it's really interesting to see, again, from a deep time standpoint, how quickly things turn into rock and how well rock record type sedimentary structures can actually be preserved. Beyond that, though, stepping out, the thing that we did here as a starting point was identify these lake beds and then survey them in to get precise vertical elevations. And then Casey did some amazing modeling work, which I've only just recently started to really appreciate how complex this is. But basically, we turned the reservoir level history on its side here so that it looks like a sea level curve of highs and lows over time from oldest to youngest. So high sand is kind of off to the right, which is how we draw ocean sea level curves as well. And through this surveying of lake beds, we know that this high up in the reservoir, water level really only reached this height at certain times, right? And so it's a simple way of trying to tell time in this recent rock record. And interestingly, one takeaway from this is that most of this 10, 12 meter deposit that we studied in detail likely got deposited over very short time periods, probably just within the high sands of the 80s, and arguably just within a few major flood events within the 80s, right? So it's drastically rapid rates of deposition over very short time periods. moving down canyon, I just can't with all these, like, it's just so beautiful. You start to see the role of vegetation interacting with sediment. So these are little, very fine scale ripples that are draped by tamarisk and other kinds of vegetation material, vegetative mats. There are root marks again, cutting through some of these sands. There's amazing soft sediment deformation. If you are a fan of mud balls, armored mud balls, there are domini balls all over the place. High energy monsoon blowout deposits, thick piles of reservoir sediment still remaining on the banks of the main stem Colorado. And here's Brenda pointing out a beautiful rotational slump fault or growth fault within the Domini. So I could go on about this stuff. Moving downstream, as we start to get into the backwater zone of the Delta, those slumps really become more and more prominent. This is from several years ago, but all of these features here in this aerial photo are the uppermost slump scarp, probably formed from lateral spreading within the reservoir sediment as the Colorado kind of incises and tries to catch up with lowering lake level. You can also see that here at White Canyon in this area. Cool things that you do see when you get into this backwater zone: flaming mud volcanoes, probably my favorite. These are sediment volcanoes, mud volcanoes that are emitting slightly flammable, probably methane mixes. Reservoirs are known for methane emissions, and it basically, we assume, is bacteria running a biogenic conversion of organic material into these shallow gas systems. Other cool stuff. So highly ephemeral, these mud volcanoes. So 1 year they'll be exposed, 1 year it's inundated again. But they're really common in that backwater zone. Other cool stuff. The returning rapids folks were all obsessed with this boulder and spraying water on it. I couldn't figure out why. And then they pointed out that they were looking at a P right there, and they had this historical photo of a Powell 1872 inscription from one of the surveys, probably not Powell himself, but someone from the survey having inscribed that. Once you move downriver, you're getting into the Delta. I love deltas as depositional systems, but they are grim places from the river perspective because deltas are this big slug of sediment that a river is forced to deposit when it starts to feel the effect of a large body of water. So its velocity slows down, the channels widen, it doesn't have the hydraulic carrying capacity that it used to have for bed load in particular, and so it drops that material really quickly. They are muddy, they are shallow, they're somewhat sketchy to try to navigate through. There's tires and trash and plastics and all that kind of stuff in them. So, but we'll come back to the deltas. That was a fast and furious view of exposed reservoir sediment in the Colorado. I'm going to jump down to the San Juan really quick. We've spent overall probably less time down there, but it's a really interesting comparison because the San Juan has a tiny bit compared to the Colorado in terms of its water discharge and annual flow, so 15% maybe of flow. But our best estimates on sediment discharge is that the Colorado and the San Juan in this area are roughly equal in terms of suspended load anyway. And that's based on some kind of 1980s era data. So that makes the San Juan a very muddy river proportionally, but one that's in the same area, same experiments being run. And so we can look at some contrasting signatures that way. The San Juan's fun because it has waterfalls that have disappeared and other ones that have appeared. This is ledge drop that silted in sometime in the late 90s to early 2000s. As this river kind of migrates and changes its course over time, it eventually decided to move over and cut into kind of friable bedrock, which created fat falls, which is a waterfall that you now have to portage your big heavy metal skiffs and big motors to get you across the lake down that waterfall. So it's a whole logistical nightmare. Our work in the San Juan in terms of the upper reaches is similar to how we've approached the Colorado. There's less exposed reservoir sediment in the banks on the San Juan, but we still have fun with really cool sedimentary structures and so on. Satellite imagery captures things like this meander bend rotation or capture over just a few days several years ago. There are methane volcanoes. They're more like little bubbling pots in the San Juan as well. So also a fun stratigraphy kind of problem. Most of the work that's ready to go to talk about in the San Juan comes from Hannah Hartley's thesis in 2022, which I'm going to publish someday. So this took advantage of those USGS sediment cores that I mentioned earlier. This is a remarkable data set. 39 cores recovered, if I remember right, and nearly 500 meters of sediment. Like, these things are so valuable. And so far, I've really only kind of looked in detail at about 4 of them from the San Juan. So as far as student projects go, there is a massive amount of work that can still be done on these cores that include some from the Colorado, some near the Escalante arm, and then the rest of the San Juan arms too. And they're gorgeous. The stratigraphy that is captured in these things, primarily pro-delta. These were, again, acquired in 2018. And so it would have been lake level history up to that. And most of the sediment was also deposited in the 80s and 90s when lake level was relatively high. But there's beautiful lamination style stratigraphy. You get this interplay between different colored stratigraphy that we have some ideas about why that is. You get this more like washed out, slightly coarser grained, silty business intermixed. And so Hannah's thesis kind of tried to tell the story of what signals are recorded in these rocks. And she comes away with a cool story about, by reading these layers, being able to pick out seasonal cyclicity, annual cyclicity, and then zooming out decadal scales of controls. And some of that is a geochemical story, and I won't get into it in too much detail, but essentially every year, so this is discharge history on the San Juan from 2016 to 2019, and you can see that there are these annual spikes that are in gray that represent annual snowmelt. And then sometimes you have high discharge events in the summer to maybe even fall associated with the North American monsoon system when it's active. And again, with the USGS, we looked at both the sedimentology, but also the geochemistry. And her argument was that you combine both of those, and it seems like the spring snowmelt, which is coming off of the San Juan Mountains in Southwest Colorado, which is a famous mining district, and lots of sort of economic geology exposures out there. So we see these slightly elevated trace metal kinds of concentrations in those deposits versus when a summer monsoon flow happens, it's more likely to be elevated in things like calcium, which we think is a detrital calcium from the local tributaries around the lower part of the San Juan. So, without getting into the details, it's kind of cool that you can look at a certain layer and say, this was spring of a certain year, right? And then zooming back out, we kind of play that same game that we did for Calf Canyon in the Colorado and trying to match timelines to the known lake level history that's shown here. And, this is her interpretation of it. Some of these we're more confident about than others, but it does appear that we can project timelines into these cores, which helps us, again, frame this idea of what were the controls, what were the signals that were active at these different times. These cores were initially taken with a question of, do we see evidence of some of the big known tailings pond mine spills from the San Juans, in particular the Gold King event in 2015. Unclear about that, but she did think that she picked up the Lake Emma spill in 1978, potentially with a little trace metal spike in one of these beds. So, very cool story kind of emerging from that. And this kind of directs us into thinking about the deltas. And, you know, if these are all pro-delta deposits, what does that mean for the main part of the delta? So kind of the last little bit of this is Brenda and I advised some Masters of Science for secondary school teachers, MSSST people, who went through some of the satellite imagery and tried to map out the location of the delta over time. And that's shown in these mesmerizing little movies that you're looking at. So here comes the Colorado Delta. And I think what shows up is how dynamic and mobile these sediment deposits really are, especially when they go into these incised bedrock canyons versus where it's kind of sitting in the bays. And again, the USGS had already sort of mapped out the accumulation of deltaic deposits in the Colorado and the San Juan over these different time periods. So putting that together, and I'll back up just really quickly and talk conceptually about what makes a delta move, like why do they actually move up and down river. And Liz is amazing. She put together these conceptual models to demonstrate this. So we think about deltas as responding to sediment supply, how much material you have coming in, and accommodation, which is the size of your bathtub. And when those two things are more or less in balance or equilibrium, your delta might be relatively stable, building up or aggregating, as well as slightly building downstream, because that's kind of what deltas do. If you tilt the seesaw back and you let accommodation outpace sediment supply, those deltas transgress. They move upriver, and in the case of the San Juan, that means moving way upriver into this little incised corridor here. They transgress, they backstep. Likewise, if you tilt it the other way and sediment supply outpaces the space you have available, then they go strongly progradational and they move across downriver across these bays. So simple, at least in principle. And when we talk about deltas in plan view, we have all these sub-environments of deposition. So the science teachers that we worked with kind of went through all of the satellite imagery and tried to find markers of exposed parts of the delta. So that includes things like the channel, the last time you see an active defined channel versus where do you see evidence of the delta front versus maybe a sediment plume that's coming out from the delta. So Brenda's working on publishing this data, which also extends back further with some additional work that we've done. This is a plot of lake elevation over time from 1999 to 2024, and these different proxies like channel end or delta front for where the delta was over time. And this is just for the San Juan, but we've done it for the Colorado as well. And what you can kind of see is like there's a decent match overall with lake level up until more recent times when you get this drastic drawdown as lake level receded quickly. And the sediment deltas are moving basinward, but maybe not as fast as you might expect. So this kind of gets me thinking about, again, this sediment supply versus accommodation. And we can see the size of these little mini basins as the deltas kind of move up and down. What's happening with sediment supply? In theory, you would think nothing, right? Because this is an impounded reservoir that's sitting downstream of other reservoirs. So you wouldn't think that sediment supply itself had changed, except that we know that local point sources of sediment are being re-entrained and sent to the delta because of these slumps. And this is a chance to highlight some kind of creative methods that we use. So this is a digital outcrop model of one of the slumps, and this is a beautiful photo of it, of a nearby as well. And I like creating outcrop models. Usually I use a drone. Not allowed to have a drone in Glen Canyon. And so this is Brenda holding on to a 30-foot painter's pole in a skiff that's motoring around, and she's just trying to hold it with her thighs. It's like a thigh master, and this thing's swinging, and I'm like, hold it still, Brenda. So we took a 12-minute video of this outcrop going up and back down the river, and I extracted 23,000 photos from this and stitched them together using structure from motion, which is fancy photogrammetry, and we created this true scale photorealistic model. And this is a basis for, if we can do this repeatedly, a basis for measuring when sediment is on the move, right? When it gets remobilized. This is another way that we try to approach thinking about how much sediment is slumping and being reactivated. So this is one of the slumps before, and then just kind of keep an eye on, I believe it's this area right here. This is after, failed rather catastrophically, and you can kind of see it's fuzzy, but the reappearance of, or the appearance of these lateral slump scarps. And back of the envelope kinds of calculations from Brenda and with help from Jeff kind of indicates that we're talking about, you know, a lot of sediment potentially being mobilized, and it has to go somewhere. Okay, so these slumps are really active throughout the corridor, and this is Narrow Canyon in Cataract, and a beautiful LiDAR image. And basically all of these little edges of the main stem here, where you see little lumps of sediment sticking out from the bedrock, all of that stuff is on the move. This is another one from Returning Rapids, the Fishmouth slump that failed last year around this time. So what does that mean? So far, we've taken you on a fast and furious tour through exposed reservoir sediment. We've talked about timelines and correlations and controls. We kind of transitioned to the deltas and thinking about what they're doing in terms of their motion over time, and then incorporating this idea of new sediment supply coming into the system under reduced accommodation. So the latest and greatest is basically looking at the subaqueous parts of these deltas. And this is with the American Chemical Society Petroleum Research Fund grant that I got. We are not looking for oil and gas in Lake Powell, so calm down. But the reason this got funded is it's a New Directions grant, and I told them that I wanted to be a geophysicist in my next life. And so they said, go for it. So here's what we're doing. We've only been able to look at the deltas in that satellite imagery from here, from what you can see exposed, and it's hard to really say much about it. So we want to be able to look under the water. And the methods that we use to do so are both sonar-based acoustic methods, right? And we either send, so with multi-beam bathymetry, we're sending an acoustic signal down to the lake floor. It comes back up. We essentially map in two-way time, sort of like a digital elevation model of the lake floor. Similarly, there's another form of sonar called CHIRP that allows you to send high-frequency acoustic pulses down into the water that actually penetrate below the lake floor and allow you to kind of look at layers beneath. And it's limited to relatively shallow imaging, but we've been able to get some pretty good stuff here. You'll notice that this is a large ocean-going vessel. Normally, that's what you would mount these instruments on. Again, Powell, you just have to get creative. So I know we talk a lot about geology versus geophysics and who's more into the hardcore fieldwork. I've done some hardcore fieldwork in my time, but I've never been more uncomfortable than on a geophysical survey in August in Powell. It was 3,000 degrees, and we are wrangling very heavy and awkward equipment that's worth hundreds of thousands of dollars that we're trying not to drop into the lake. Again, Mike Dehoff, returning rapids, creates these booms with a saw at the boat ramp, trying to get all this stuff situated. Absolutely amazing. So we are leveraging some previous surveys that I mentioned at the beginning in 2004 and 2017, multi-beam bathymetry surveys that covered the whole lake as well as the two main deltas. And then last year and this past August, we did some additional surveying in the San Juan and the Colorado arm. And this is what Emma Crease is working on for her master's thesis. This is some of our 2024 CHIRP data looking at the sub-bottom imaging. This is the lake bottom, so I've cut off all of the water column above. And probably if you squint, you can start to see some interesting layers and relationships here. The depth is in two-way time, so I can only estimate in terms of meters based on some velocity assumptions of the sediment. But basically, if I start to kind of get my colored pencil out and play around with this and interpret it, I start to see some distinctive acoustic layering within the stratigraphy that is likely reservoir sediment, possibly even going down to kind of the pre-dam Colorado channel in some cases. So we're still, this kind of data takes a lot of processing and takes a while to fully dive into. These are just some other images. This is a long line down the entire San Juan Delta. This is the lake bottom showing that pro delta sloping down. What's interesting on these is that we often see this washout zone, especially really close to the deltas, where you really lose all signal for a couple meters at least, probably, until it gets down lower. And our thoughts on that, very likely there is gas, and we've seen that in these methane volcanoes, and the deltas are bubbly, so you can see gas coming out of the lake floor here. So that might be part of this washout zone. We've also started to think about fluid mud, and that's become more of a daylighted thing that we're aware of. And what fluid mud is it's nasty. It's highly dense, concentrated slurries of sediment and water. And because it's so concentrated, it has these properties of sort of like the base of a turbidity current, where the very base of it is basically plastic. It's sort of moving along as its own semi-cohesive bed. And what that means is that sometimes these currents can reach way out beyond the pro-delta, so getting way out into the lake. This is some of our multi-beam data. We haven't seen this exactly yet, but in a 2004 publication, some folks showed multi-beam over several days. They showed actually flowing currents at the lake floor of sediment. So stay tuned for that. What we've mainly focused on is looking at bathymetric profiles so far from the multi-beam. And so this is kind of our version of the USGS Delta profiles, in this case for the San Juan. And what we've added here in blue, so we've simplified the time scales to just these 4 or 5 main intervals, but in blue is basically what has been accumulated in the pro delta since 2017, right? So the San Juan is kind of really spread out. It's got a complicated kind of bathymetry to it, but there are kind of these 2 main pods. And if you zoom in, it's actually a fair amount of sediment, especially when you consider we're talking about just, the last 7 or 8 years versus the previous 40 to 60, right? Same thing, and actually even more exaggerated in the Colorado. Here's the current Colorado River pro delta with, again, fairly significant, in some cases 10 or 15 meters of additional sediment in the last 8 years versus maybe 30 in the previous 40 years. So potentially accelerated rates of deposition in these deltas. And again, it's if you project in kind of modern day lake level, all of the stuff above the line here is exposed and is subject to remobilization. So it gets back to that sediment supply issue of we need to be thinking about internally what's coming into this, not what's coming from outside of the system, but what is already within the system. So I'm more or less going to leave it at that. I have a long wish list of other things I want to do. I appreciate the records that we have, but I want better. So I want repeat monitoring. I would love to be able to fly a drone. That would make our lives much, much simpler and probably safer. But this is kind of where we're headed with a lot of the current research is really kind of looking at that remobilization of sediment and what effect that is going to have on these deltas. We're trying to keep sediment in the conversation. There's no question that it's not necessarily the main question with Powell. Water is still king. But we're starting to have some thoughts about, is there some application of what we've learned about the deltas? And I put this at the end so that I wouldn't talk about it because it's controversial. If you want to ask me about it, I'll go back to it. So I'll just end with this. I'm not at the table, and it's a good thing, making decisions about what's going to happen in 2026, but decisions need to be made. They have to be made. And there are all different kinds of plans on the table. Utah State has a fill mead first plan that, kind of says mead is the main reservoir, and Powell is sort of what leads to that. There are, of course, some folks who want to get rid of Glen Canyon Dam entirely. I love coming full circle to these images. These are back of the envelope, literally on a napkin, sketches by Floyd Dominy himself. And this is recounted in a Salt Lake Tribune article where the co-founder of the Glen Canyon Institute is talking to Floyd about what do we do. They didn't build a drain hole into Glen Canyon. They filled the bypass tunnels that were originally built here with concrete. And Floyd says you can't go into that. You need to create new bypass tunnels to kind of mitigate what's happened thus far in Glen Canyon. And then he goes on in this article to think about the fact that Grand Canyon is what's sitting next below. So these are some of the things that are on the table. And like I said, we're just really trying to keep the sediment story as part of that conversation and just trying to learn from this experiment as much as we can. So here's the promised very long list of folks who have been involved so far. Lots of students here at the U and lots of great colleagues at all of these other places. And I'll stop there. Thank you. Just a couple minutes, yeah. Yep.
Change supply of sediments. That data?
As far as I know, sediment discharge goes up to about the 80s. It's an 84. I'm looking at Casey. 1984 Thompson study. And I guess the thought is that that was around the time that the new dam stopped being built. And so we kind of assume that it hasn't changed from external supplies very much. Those upstream dams seem to be doing their job. They are also impounding sediment. So what's getting, like I like to think about grain size partitioning in this scenario, because I think pre-dam Colorado had its own kind of sand versus mud, bed load, suspended load kinds of sediment distributions. My sense is that we are preferentially holding on to the muds here. And so when we think about, and this is way beyond what you're saying, but Grand Canyon has a sand problem. They don't have enough sand in the beaches and so on. And so part of the sediment story is, well, what happens if we could somehow release sediment downstream? And the scientist says, we need to think about how much of that is really sand versus mud and what's going to happen if we do that. So long-winded answer, but my guess is we don't think it would have changed drastically since the 80s.
Classic.
Mm-hmm. Why is it white? Yeah, those are the. Yeah, the bathtub ring. Um, Fairly extensive from what I've seen. There are multiple. I would say in some cases you can see the very high water line is really starting to fade. And you're kind of just looking at that difference between long-term exposed desert varnish, basically, and sometimes seeps. Um, the water line, at some point in time, I can't remember when the quagga mussels were introduced, but at some point in time, when you look at that water line, at least more recent ones, it's all got these little mussels tied to it. And it's also I think a carbonate sort of rind that gets plastered onto it. So, yeah. Marty. Yeah. Yes. So there was a hasty survey done immediately prior to inundation where they sort of marked what they could get to as far as known sites. Um, as water level is going down, going back to some of the known ones, it's sort of a mix. Some of them have been completely destroyed. Some of them, there's still like some evidence left. But that's actually one of the proposals that Brenda and I put together. We asked the state archaeologist, we gave him a footprint and said, if this is our study area, you know, how many sites would we potentially need to worry about? Because there's rules about permitting and what kind of science you can do. And it was a fairly small field area in Cat Canyon, and it was like hundreds of known sites in this little area. Um, so I think the full recovery in that sense has yet to be seen. I'd like to remain optimistic, but the reservoir sediment has a pretty drastic effect when it encases even bedrock. So I'm not sure. Yes, probably last one, so you all can get along. Mm-hmm. That's possible. I think what we're poised to do is some fairly simple numerical modeling efforts around what happens um, with sediment supply and accommodation. And like basically what I was getting at with this is the deltas are highly mobile when it's a confined zone because there's not accommodation to work with. They just have to move. And Alan Kasprach and some ecology type folks have demonstrated that it's the movement of the delta over a year kind of time scale that's really destructive to native vegetation and so on. And the deltas are just hard to deal with. And so, yeah, in my mind, I think there is a way that we could think about can we can we mitigate the destruction of these mobile slugs of sediment by keeping them in the bays? They're going to fill in anyway. Can we kind of agree to a certain water level that allows us to fill in a bay before sending it all the way downstream? So I think that we can get around that idea of how quickly is it going to move, but we need to have some idea of what water level is going to be. And that's all managed. So it's doable. I don't know if Park the Deltas is going to be the thing, but I think that it should be part of the sediment management story. Okay, I should let you all get on to your other lives. Thank you.